We're supposed to state the domain, the vertical asymptote, and the end behavior of this function here. An important idea with logarithms, like if we just look at a more simple logarithm, a log base 10 of x, and just in case you're not aware, if there's no number written here, then you could write in a base 10. It's just like a convention that if no number is written, then the base is 10. And what a base says is it says like what power do you need to raise the base to make it equal x? Okay, so maybe if we don't do a variable first, a quick example, log base 10 of 100. If you were to plug this in your calculator, it would give you 2 because you need to raise 10 to the power of 2 to make it equal 100. Okay, so this logarithm, it doesn't have a little subscript down here. That means we can write in a 10 if we want. Okay, it's implied that it's 10. Sometimes you'll see log base 2, sometimes log base 3. Okay, and with this logarithm, it's saying what power do you need to raise 10 to make it equal some number x? And so there's a restriction on those numbers, those x numbers. Look, because if you start with a base positive 10, can you ever make it negative? You know, can you ever pick an exponent for 10 to make it turn into some negative number? If you pick like a -4, a negative exponent doesn't change the sign of a number. It just means you could rewrite it as a reciprocal. It's making it really, really small. So with logarithms, you can't change. You can't put an argument that's negative in here because you can never get a negative number out of a logarithm. And similarly, can you get a 0 out of a logarithm? Can you ever find a number to raise 10 to the power of something to make it equal 0? If you do 10 to the -1,000th power, you see it's a really small decimal, but you can never actually reach 0. So with logarithms, we're looking at the argument. We want to make sure that this doesn't equal 0. And we want to make sure it doesn't equal negative numbers. So a quick thing you can do is with logarithms, when you're trying to find the domain, you want to say the domain is when the argument of the logarithm is greater than 0. Okay, so if you solve this inequality, you get x is greater than 7/3. And so that's our domain. In interval notation, we put a parentheses, 7/3, and then comma, infinity, because it can be as large as you want inside the logarithm, as long as we don't have a 0 or a negative number. X equals, it just says x equals here. Probably needs some extra clarification. I think what they want here is the vertical asymptote. Where does the vertical asymptote happen? In the logarithm, it's at 7/3. Because if you were to graph this logarithm, you can get infinitely close to 7/3 on the for the x value. But this is where it starts going to negative infinity. Okay, you never actually reach 7/3. You can get infinitely close to it by plugging in bigger and bigger numbers. Sorry. You can never reach x equals 7/3. If you were to graph this in like Desmos and graphing software, it makes a vertical asymptote because this is like the cutoff zone, right? If you were to plug in exactly 7/3, that would make the argument be 0, which is something that you can't get from a logarithm. Oh, and sorry, for this graph, it would be a little bit different because it's negative log of all this stuff, so the graph would be going in a different direction than what I have here, but it'd still be a vertical asymptote. Okay, you got 7/3, get infinitely close. It's got +4 as well. Yeah, just make sure in tests that you don't refer to, just say like I plugged it in graphing software. I got to give some sort of like numerical or algebraic reason for why we're making a choice. So I actually accidentally deleted this one. It was cleaned up the last slide, but we're working on this part here as x approaches the vertical asymptote. Okay, so with this function, we said we can have nothing less than x equals 7/3. That was our domain, right? And so if we compare this to the graph of log of x, like what sometimes we call the parent function, it's really negative infinity, and then it starts leveling off over time a little bit. Okay, but we're multiplying the result of the logarithm by -1. So all these negative numbers are being multiplied by -1, so that makes them be really positive. Okay, so the graph is going to look something like this. And eventually it'll level off. The +4 bumps us up a little bit from the original graph. If we were to flip this graph, a +4 bumps us up higher on the y-axis, but it's a logarithm, so eventually it will come down below +4. So this is a rough sketch of the graph. Okay. The big idea for the vertical asymptote part, though, we don't need to have everything to be really accurate in the sketch. We just need to know what's happening to the y values. H of x are like the y values of the graph that you have. And as x approaches the vertical asymptote, which means as we consider values as we get closer and closer to the vertical asymptote, think about what's happening to the y values. They're going up, right? They actually go up to infinity. The y values have no upper ceiling. They just keep going up and up and up. Okay, and that again comes from the fact that we're multiplying by -1. So we're thinking about the original graph of logarithm of x, and every original value is getting multiplied by -1. It gets shifted a little bit too, but the important part is that we're going to positive infinity instead of negative infinity. Then here you have some options, negative infinity or positive infinity. We don't want to choose negative infinity here because as x approaches negative infinity is going in this direction, right? The graph has no behavior over here. The graph is cut off by this vertical asymptote, and there's nothing to analyze over here because the function doesn't exist as x approaches negative infinity. So you want to analyze as x approaches positive infinity. What's happening to h of x? It looks like it might level off at +4, but you've got to think about the values that can possibly come out of this logarithm. Right? As x goes to positive infinity. So think about really, really big values for x. Okay? Then you have 3 times like a billion, and 3 billion minus 7 is still a really large number. You take a logarithm of that, it's going to shrink it a lot, but it's still going to be very, very large, and then you negate it, so you got some sort of negative number added to 4. What's happening is as x goes to infinity, you're taking a bigger and bigger negative number and adding it to just a constant 4. So this goes towards negative infinity, and negative infinity is going to swallow up just a puny little +4, right? So it doesn't look like it if you just check it out quickly in Desmos, but with logarithms, they slow down, but they keep decreasing or they keep increasing over time. This will eventually go towards negative infinity on the y-axis. So let me help with typing those in. The domain, I'm going to put parentheses, 7/3, and then I think lowercase I for infinity. Okay, that's our domain. The x, they should probably put an extra piece of information here. The vertical asymptote is x equals 7/3 we found. As x approaches the vertical asymptote, h of x approaches positive infinity we saw with our sketch. And as x goes towards positive infinity, we went towards negative infinity. And you can click on these little things just to make sure the symbol's right. I think that's everything.